Welcome to Gravity Engine Tutorial 2, where we'll talk about some of the orbit features in the gravity engine. We'll begin here with a scene that has an instance of the gravity engine with the default parameters. We've placed a star with an attached model in the scene, and the star has a mass of 1,000 and is located at 0. And for a little bit of background, we've added a particle system that provides a hemispherical star field background. Now we'll add a planet. And so in the prefabs directory, there's a planet, which is just an object with mass of 1 and an n-body script attached. So we'll take this and we will make it a child of the star. And the planet ends up at a position 10. Now if we want this planet to move around the star, we could go over here and add a velocity and experiment with the velocity to get the exact path that we want around the star. But there's a component in the gravity engine that automates this velocity calculation based on the orbit we want. So what we do is we add an orbit ellipse component, and the orbit ellipse component detects that the planet is the child of a star, makes the star the center object of the orbit automatically. You can change that in the editor if you wish to. And then it provides a series of parameters for the orbit. So the size of the orbit is controlled by the axis dimension here. We can change that. We can change the eccentricity of the orbit. It begins as a circle, but we can deform it into an ellipse. And we can control the orientation in space with these three parameters: large omega, little omega, and inclination. So inclination tilts the orbit out of the plane of xy. This is a rotation around the z-axis. And then when there is an inclination, little omega is a rotation in the inclined plane. We can also control where in the orbit the body starts by changing the starting phase. And if at this point we press play, we see that the object is given the correct initial velocity to move in the orbit that was shown to us in the scene view. Now it can be useful to have the orbital path in the game view, and there's a way for us to do that by taking this orbit path prefab and making it a child of the planet we want to see the orbit for. So if we look at that, what we see is that there's an orbit renderer that looks at simply takes as a parameter the number of points we want to use to draw the path. There's a line renderer where we can specify a material and a start width and a finish width. Make this width just a little bit thinner here. And now if we press play, we can see this blue ring which shows the path that the body will take. And if we change the shader for that, we can enhance that blue ring, make it a little bit more visible. Now we can see the planet following the orbit. The important thing to remember with orbits is, even in the case of our own solar system, the planet masses are a very small fraction of the mass of the central object. For example, Jupiter is about 1/1000th the mass of the Sun, which is why I've made the star 1,000 and the planet 1. You can see a much smaller sphere here drawn around the planet. This is called the Hill sphere, for those of you who like celestial mechanics terms. And what it's showing is the region around the planet where the planet's gravity would dominate. So this allows us to, if we wanted to have a moon, we would need to place the moon inside this sphere here. If we make the planet heavier, then that region of influence will expand, and so if we take the planet and make it, say, 30, we can see that there's now a much larger region in which the moon could orbit. If we press play now and look at the renderer, what we'll see is because we've made the planet heavier, it's actually not exactly following the ellipse that's predicted, and that's because the central object has started to drift a little bit because we've added some velocity to a fairly heavy object out here now, a heavier planet, and the center of mass of the entire system has a drift velocity. If we wish to eliminate that, we can add a component to the star called fixed object. And what that says is that this object will not be affected by the gravity and it will be anchored, but its mass will affect others. And that will remove this drift component, which can be quite handy if you're building a solar system with multiple planets because you'll get a fairly complicated behavior of the central object. So ellipses are one type of an orbit where the energy is such that the body can't escape from the star. There are other orbits, which we can illustrate by taking another planet, making it a child of the star. And now we can add a component called orbit hyperbola, orbit hyper. What we see here is the path that would occur if the object was coming from infinity, swinging past the star, and then escaping. We can again control the shape of the orbit with parameters. There's an eccentricity. For a hyperbola, the eccentricity will have to be greater than 1. And the larger you make it, the flatter the orbit is. If we change it to 10, we get a very flat, slight deflection body. We can change the starting location by changing the initial distance. So you can see here the body's out here. We'll then come in and move past this closest approach point near the focus and then continue outward. If we press play, you can see that orbit happen. You can also attach an orbit renderer to the ellipse and see the path of the ellipse in the scene view if that's something you want to do. Now we'll show the hierarchical nature of the orbit system by taking a planet with an orbit attached, making it a child of the planet we already have in the scene. To make this a little more obvious, we'll call this planet Moon. And as you can see, it has an elliptical orbit attached. We'll change the mass of the Moon to 0. And we'll go back and look at the planet here. The planet. We can see that where we've placed the Moon is outside the Hill sphere of the planet. So at this distance, the Moon won't stay in orbit around the planet because it's not at a point where the gravitation from the planet is dominating the gravitation of the star. So let's move the Moon inside the Hill sphere by changing its radius to, say, 2.5. So now when we look here, we can see the Moon is inside the Hill sphere. Bear in mind the Hill sphere is the point at which the force of gravity from the planet and the star are equal. And it doesn't mean that the Moon will necessarily stay bound, but if it's outside the sphere, it will definitely not stay bound. So you very often need to move closer than the actual diameter of the Hill sphere, which is why I've picked 2.5. So if we now play this scene, we can see that we have a planet moving in an orbit, and that the orbit is in fact not exactly the orbit we saw in the editor view, and that's because of the gravitational influence of the central star. But it is staying in orbit around the planet. If we wanted the orbit of the Moon to be exactly as shown, to follow this path, disregarding to a certain extent the laws of gravity and basically ignoring the field from the sun, we can do that by saying don't use gravity to evolve this, just use Kepler's equation, which is saying follow this path around the star. And There may be good reasons to do this in your game. This may be the orbit you want to have. And then if we play, we now get the planet moving in its uniform orbit around the star. It's not obeying exactly the gravitational equations, but it might be the effect you want in your game. So you have that option. And that's the tutorial on orbits in the gravity engine. Thank you for watching.